Welcome back. Now we are going to discuss the other type of asymptote that these rational functions may have, and that is the horizontal asymptote. We have also seen this one before with the function 1 over x. We know this has a horizontal asymptote at y equals 0 because it approaches the x-axis from below but never quite gets there on the left, and approaches from above but never quite gets there on the right. So to describe this behavior, we would say that a function has a horizontal asymptote at y equals k. It's going to be a horizontal line. And this is the asymptote if, as x approaches either positive or negative infinity, so as we go off to the left or off to the right, infinitely far, our function's value will approach the value k. So again, that definition is nice, having that notation that says as our x value gets infinitely large or goes off in the negative direction infinitely far, our function is settling down to a constant value. Now, this talks about x going to infinity and negative infinity. It does not say anything about local x values. So our horizontal asymptote is an eventuality, not a local phenomenon. And I'll explain what I mean by that in just a second. So we mostly care about finding these. So if we have a rational function, there are a few possibilities. And here you'll see that I've written out my rational function so that the numerator and denominator are expressed as polynomial expansions. Here I have my leading coefficient, my highest power of x in the numerator, and so on. And in the denominator I have my leading coefficient b sub n and x to the n. This is an nth degree polynomial, so maybe x to the fourth, and so on down the line from there. Now, the way that we are going to figure out what the situation is with the horizontal asymptote is we are going to look at the leading terms. So a sub m x to the m, whatever that might be, and b sub n x to the n. We don't really care about the rest of each of these polynomials. We are just going to look at the leading terms in the numerator and denominator. Okay, so case 1, if the degree of the numerator, that is this power m, if m is less than n, less than the degree of the denominator, so if there's a higher power in the denominator and a lower power in the numerator, if that is the case, then the horizontal asymptote will be y equals 0. Okay, so very little work involved there. If this is the case, we compare our degrees, then the x-axis will be the horizontal asymptote just as it was for 1 over x. Now, if the degrees are equal, if m equals n, if this is if the degree of the numerator and the degree of the denominator are identical, then we need to do a little bit more work. Then we would take those coefficients and we would say our horizontal asymptote is going to be at a sub m over b sub n. In other words, whatever the coefficient of the numerator is over whatever the coefficient of the denominator is. Okay, so those are two situations we may encounter. The third is actually kind of nice for right now if the power or the degree of the numerator is greater than the degree of the denominator. For instance, if I had a cubic over a quadratic, then we say that there is no horizontal asymptote. So we'll leave it at that. We'll say there's no horizontal asymptote. So, no horizontal asymptote to worry about in this case. The two cases that we are going to concern ourselves with for right now are case 1 and 2. Now, we will talk about what exactly is going on when the degree of the numerator is greater than the degree of the denominator, but that will have to wait. So let's get a little bit of practice using these ideas. We want to find the horizontal asymptote for each of these functions. We'll start with f of x equals 3x to the 4th plus 2x, all over x to the 6th minus 1. So all I need to do is look at these powers, the 4th power and the 6th power. So the power of the numerator is less than the power of the denominator. And so I would say that y equals 0 is our horizontal asymptote. Easy as that. Now for our second one, we have equal degrees. The numerator and denominator are both second degree polynomials. So I need to do a little bit more work. I'll say y equals, it's going to be a horizontal line. And then I'll take the leading coefficients, y equals 2/3. Is going to be the location of that second function's horizontal asymptote. Now it is worth noting at this point that there will only ever be one horizontal asymptote for a rational function. A rational function will only have at most one horizontal asymptote. So it may have none, or it will have one and only one. Now, as I mentioned before, rational functions' horizontal asymptotes are a concept of infinities. When x is very, very large, eventually our function will settle down. But locally, our functions can cross their horizontal asymptotes. So to see how we would handle that, or see if it's occurring, we will check with this function and see, does this function, f of x equals x squared minus 3x all over x squared minus 5x minus 6, does this cross its horizontal asymptote? So first, if we're going to answer this question, we need to find its horizontal asymptote, if it has one. Now we compare the degrees. This is a degree 2 polynomial over a degree 2 polynomial, so our horizontal asymptote is at y equals 1 over 1. In other words, y equals 1. Now, the way that I determine if this function crosses is to ask, is my function ever at a height of 1? In other words, is my function ever equal to its horizontal asymptote? So that is going to be how we handle these. To determine if a function crosses its asymptote, we set the two equal. Now, our function will never cross its vertical asymptote because Well, functions simply don't do that. The vertical asymptote occurs because there is an x value that we are unable to plug in. Now, if we were able to cross our vertical asymptote, it would not really be an asymptote. We would eventually have to exhibit some sort of behavior that would fail the vertical line test and make our function not really a function. So in this class, you never have to worry about something crossing a vertical asymptote, only these horizontal asymptotes and one other type that we'll see in just a little while. So I set my function equal to its asymptote value, and then I'll try to solve. I'll see, is there some x value that makes this happen? Now, what I have here is a rational function that I need to solve, and I can do so by multiplying across by x squared minus 5x minus 6. So, is it ever the case that x squared minus 5x minus 6 equals x squared minus 3x? Well, if I try to simplify this, maybe get one side equal to 0, I would find my x squareds actually disappear, and negative 5x plus 3x gives me negative 2x. So if negative 2x equals 6, that happens when x equals negative 3. In other words, we have in fact found the location where our x, or where our function is equal to its horizontal asymptote. In fact, the point negative 3, 1 lies on the graph of my function, and this is where my horizontal asymptote and my function cross each other. Now this piece of information is going to be very helpful later on when we actually start graphing these functions, so make sure that you're comfortable with the idea involved here. You find your horizontal asymptote first, and then to check whether it crosses, you set your function equal to your horizontal asymptote.